AP optics problems. First one, we have a light ray going into plastic. They're asking us to determine the speed inside of the plastic. That comes from this relationship. This is the definition of what n is. It tells how much does the speed of light slow down inside of that material. To get n, we're going to have to use Snell's law. So let me redraw the picture here, air going into plastic. The first thing we do on every one of these problems is draw in the normal line where the light ray hits the surface. That's where it's going to be bending. The purpose of the normal line is to measure the angle from. That angle is 53 degrees, is the angle of incidence for the air. And then we need this angle for the plastic. Those are the two angles we use for Snell's law. In this case, we're looking for the index of refraction for the plastic, so we're going to divide by the sine of the angle in the plastic. So it looks like that. I'll plug in our numbers, and I got 1.33 for the index of refraction. Then I can plug that in down here in the speed formula, and we're dividing it into the speed of light. It comes out to 2.3 times 10 to the 8 meters per second. Another way to write this is 0.75 times c. They will allow you to use a fraction only when you're multiplying by c. All other problems you have to divide it out. The second part, determine what will happen to the light ray on this side. How is it going to come out? Again, we're going to use Snell's law, and we're going to start with this angle. We have to use alternate interior angles to figure out that this is 53 degrees. And this time we're going from plastic into air, so we want theta air. So we're going to divide by index of refraction of air and do the inverse sign. We plug in the numbers, and we get an error because we're trying to take an inverse sign of a number larger than 1. And what that means is that this angle, 53 degrees, is larger than the critical angle for the plastic. When that occurs, no light ray comes out of the plastic. It bounces back inside. That's called total internal reflection. And the light ray will reflect at the same angle of incidence, 53 degrees, 53 degrees. Next one, we're looking at how the light rays bend, but this time we're starting in the plastic and we have a lens made out of air. Now we know that light rays, when they come straight onto the surface, when they're perpendicular to the surface, they do not bend at all. At this end, what I'm going to do is draw in a normal line for each of the light rays. And we know right when the light ray gets to the normal, that's when it's going to do a bending. So I'm going to start by continuing these straight. I know this middle one is going to stay straight because it's perpendicular to the surface right along the normal line. The ones on these two sides are going to bend. If we're going from air to plastic, we're slowing down, and that means we bend towards the normal, so bend outwards. That makes this lens a diverging lens, even though the shape is convex. Next, drawing our light ray diagram. We only need two rules. Since they didn't give us what C is, we're only going to draw two light rays. A light going in parallel goes out through the focus point, and light going in through the focus point comes out parallel. The light rays come from the tip of the object, so we find the tip of the image to draw in where our image is. Is the image real or virtual? This is a real image. I recognize it's real because it's inverted. However, when you're explaining that, you don't say because it's upside down. You say the real image are where the light rays converge. If the light rays converge, that's what makes it a real image, and that's the definition of what a real image is. Is the image located right or left of the mirror? Real images have to be in front of the mirror, be on the left side. Calculate the position of the image. They gave us the distance of the object and the focal length, so we can use the lens formula. 1 over di equals 1 over f minus 1 over do. That comes out to 15 centimeters, and then we're rounding for one significant digit, is 20 centimeters. Calculate the size of the image. We're going to use the relationship for the magnification. We're looking for the height of the image, so I'm going to multiply both sides by ho. And we plug in the numbers, cancel the centimeters, minus 3 centimeters. 3 shows us that it's half the size of the original, and minus means that it's inverted. Indicate on the diagram how a light ray at point P to Q is reflected. We know that all the light rays that come from the tip of the object have to go to the tip of the image. The only ones that go through the focus point are the ones with a parallel side. Neither of these are parallel, so they will not go through the focus, but they will always go to the tip of the image.